So hi everybody, thanks for joining us. So Dr. Eduardo Santos will be presenting this month's all-time this meeting presentation, and his title is Effect of Heat Wave and Drought on Evapotranspiration and Carbon Fluxes in a Cornfield. So Eduardo, the floor is yours. Go ahead.
Okay, well, thank you. See if I can. Is everybody able to see my screen here?
We can see your screen.
Okay. Yeah, so what I'm going to present today is, okay, so this presentation is basically divided in two parts. I think not everyone here is familiar with micrometeorological methods, and so I thought of giving people some background on the techniques, and also present very preliminary data. So we actually finished collecting data last week, and this was done in Gibson at Justin Knox, one of Justin Knox field. So we're gonna show some of those results here. That was like quite interesting year because we had that heat wave, maybe like a month or so ago. So, all right. So let me start here. So the just thinking about the process of the turbulent process of transporting mass and energy. So in plant canopies, most of this transport is done by turbulent eddies. So you have the main wind, and then because there is some friction with the surface, and also there is during the daytime you have some difference in density of air. You have the formation of those eddies, and these eddies they transport the majority of mass and energy in these systems. There is actually an interesting calculation that if you didn't have this turbulent transport during the daytime, pretty quickly you get this boundary layer here close to the surface depleted in CO2, because the plant CO2 would uptake all the CO2 that's available there. Okay, so we can take advantage of that this phenomenon to estimate or measure fluxes at this close to the surface layer. So the way we can think about is that the main wind is carrying some molecules, but there is also some molecules that are carrying upwards by these turbulent eddies. So upwards and downwards, so you have these vertical motions. So then if you look at the time series of vertical wind velocity, so I'm just looking at the data. Usually, most weather stations measure horizontal wind, but you can also measure the vertical wind. So if you look at these eddies, you can see here that two time series in this graph. One is W here is the vertical wind speed, which is blue, and then the green here is the CO2 concentration. So I'm gonna just draw your attention to these circles here. So you see here, as the wind departs the surface at night, or as if you have like an air parcel leaving the surface at night, since there is no photosynthesis at night, you're going to have a positive increase in CO2 concentration. Now, if the wind is coming down, meaning like bringing air from the top of the from a layer above the canopy, you're going to see a decrease in that concentration. Okay, so this is at the night time when you have a CO2 release. Now, during the morning, you have an opposite effect here. So you see here that as the wind going up brings like air from the bottom of the canopy up, you can see that there is a decrease in concentration at the point that you're observing. And then you see this throughout the time series, like you can highlight this. So then that's an indication of CO2 uptake. So you can use this covariance. So the covariance between these two signals here, a concentration and a wind velocity, is then proportional to a flux of a given entity. Like it could be CO2, water vapor, N2O, methane, or even temperature. Like you get an increase in a sensible heat flux. So that's why that's why we have this name eddy covariance, because this technique is based on this covariance between these two signals. So as to okay, that's better. So so next one. So here, then, so if you measure then the turbulence, water vapor concentration, and actually CO2, you can determine how much water or how much CO2 is uptaken by crops. So you can see here, this is like a picture here of eddy covariance tower. So you usually is done in the middle of a large field. So this is, I'm going to explain, why it's not suitable for small plots. But you can monitor this gas exchange over long times and then at a very high frequency. Okay, so this is some of the sites that do these measurements throughout the world. So this is I got from FluxNet. It didn't have an updated map here, but so I used this one. So you see here that all these triangles here show points that they are monitoring these fluxes. Most of them located in North America and in Europe. And most of them are located in over natural vegetation. So, but there is a few sites that are monitoring gas exchange over crops. Okay, so why there is some advantage of measuring these fluxes, or namely like evapotranspiration and CO2 flux with eddy covariance. One is like this non-intrusive method. So you basically have a tower with a small physical footprint that's over a relatively large area, and then you measure the flux without affecting the soil that you're measuring or plants. That's not true for like if you do chamber measurements, like as you're putting a chamber on top of the soil, so you're suppressing some of the important processes that are related to gas exchange. For instance, like you putting a chamber over the soil, if you leave too long, it's going to start heating up that surface, and that would affect your fluxes. So you can simultaneously measure CO2 and water vapor fluxes, and now I have to say in other gases as well, as long as you have the analyzer to do these measurements. And then you could improve remote sensing algorithms to estimate ET or now satellites estimate carbon uptake by vegetation. And the reason you can do that is that you see here, this is a map showing the temporal scale and then the spatial scale of different techniques. So if you like similes here that are used to direct measure of ET, and I should have include here chambers as well. And then this is like a local level, very small subplot level. Now the eddy covariance here, another micrometeorological approach, is you actually in the plot field or site level. So you see here, and then you're measuring this over continuously. So you have a good spatial coverage, and then you also have a good temporal scale coverage. So you measure those fluxes over a long time, and then with high resolution. Now the remote sensing techniques, they can measure a very much larger scale, but usually what you have is that you don't have such a good temporal scale. So the satellite would pass, and then you get an image, and maybe in a week or so you'll come back, and then you get another image. But the nice thing here is that there is an overlap here, so you could perhaps use this micrometeorological approach in conjunction with remote sensing techniques to improve the coverage of both methods. Okay, so main challenges of using, so usually, well, with eddy covariance, you requires high frequency measurements. So you measuring what at least 10 data points per second to capture the transport of those edges that I talked about before. The instrumentation is I would say relatively expensive, and then it requires process of large data sets. So just giving an idea here, so 30 days of data with a typical eddy covariance system, you're going to generate 5 trillion data points. So you need to take that, store it, make sure that do some quality data quality analysis, and then process all the data. So what else can you do with this data? One of the aspects that you're trying here is like doing evapotranspiration partitioning. So you have here measurements, these measurements of ET on the top of the canopy. And then the ET is actually having this combined signal of plant transpiration and an evaporation from the soil. Why should you partition this? One of the reasons why is that so if you want to understand more about these processes, you need to partition, because the variables governing transpiration are different than the variables that are governing respiration. So by grouping everything together, it's hard to come up with a good model or method to study these drivers. Similarly, like you have CO2 fluxes, so you imagine CO2 flux here, net flux on top of the canopy. But this flux here is a combination of plant and soil fluxes. So again, variables governing those two fluxes are different. Okay, so now I'm going to move on to the experiment that we conducted this summer. So we have this tower here for like a few years now, running at this field site in New Gypsum. So Justin Knopf is the one that's farming this field. So the farming system here is no-till. You can see here, this is right after they plant corn this last May, when you deploy the tower. And then this flux measurements were done here from May to September 2023. So you see here that we try to deploy the tower close to the center here of the field. And the reason why is that you want to, if you put too close to this border here, you might get some measurements from this adjacent field here. That's not the point. So the point here is you want to make sure that the area influencing the measurement is actually within this field. Okay, so so here just some of the data for this summer. So here I have precipitation and then the reference CT. So this was obtained in a weather station is about like 2 miles from this site. It's the Mesonet station at Gypsum. Sorry. Oh. So here you have a reference CT for alfalfa and precipitation. So what you can see here is that the amount of, so let me just give you a little bit of feedback on what's reference CT. So reference CT, it's the evapotranspiration for a hypothetical surface, in this case here, like you mimicking alfalfa, growing under conditions that you don't have water stress or any other stress that would affect the ET. So under these conditions, the ET is only a function of meteorological variables. Okay, So then what you're doing here is that you're removing the crop and soil components here of this ET. So why you use this is that you can use weather data to estimate this, and by applying crop coefficient, you can take that measurement and then convert it to ET for a crop. We haven't done this for corn yet, but that's one of the next steps, is just look at what would be the ET for the corn and then compare with our measurements. But what I want to show you is that this is a cumulative type of graph, and then you can see here that the precipitation is lagging behind the ET. So that indicates that you have a water stress, right? So in order to if you didn't have water stress, you would have you have to have ET. What you're losing with evaporation in theory should be equal to what you gain with precipitation. Okay, so here's some flux data collected by the tower, and then you also have some environmental variables here. So you see here, this is air temperature. So this is, I just took a sample data for it was 4 days here. So here's a typical daily trend. So you go, temperature goes up during the day, and then you see here that ET is going up, and then during the day, and reach its maximum here close to noon, and then it comes down again, and then at night it's close to zero, and then again it goes up and down. Well, this up and down is mostly driven by the amount of radiation that you have in the system for evapotranspiration. Similarly, you see here that the CO2 flux. So you see, one thing I want to point out here, that you see that there is a negative scale here. So the negative scale is just a convention. So in this community, like micrometeorologists, they usually use a negative convention to feed the fluxes going towards the surface. So if the plants are taking CO2 here, you're going to get a negative flux, and then if they're releasing CO2, you see a positive flux during the night, and then it goes like this. All right, and then I just want to mention here that you have some days that you have low fluxes, and then mostly what happened here is that you have cloudy day, so you don't have as much energy to drive just 2 fluxes. And you can see here the temperature also didn't change much. Okay, so this is just a sample. So each data point here is a half an hour value, and then we have sometimes you see things like this. So what usually happens is that you don't have enough turbulence at night, and then you need to do some screening to remove these data points here, because you get more uncertainties when in nighttime periods, when you don't get as much turbulent transport. Okay, so now let's look at the entire growing season, how it looked like. So you can see here, so we have air temperature and then VPG. So VPG is the vapor pressure deficit. So what's VPG is telling you is what's the drying power of the air. So a higher VPG would usually increase the water used by plants. Okay, so at some point, the VPG is so high that the plants will just close the stomates and to prevent water loss. So you can see here in the top you have ET. So the planting occurred here at May 1st, and then in about a week we had everything up and running. So you didn't miss much. The plants were still germinating. If you remember that picture there, we didn't have the leaf area index was actually pretty low. So you see here that most of the time here during this period here, you can still have a higher water flux, but most of this, and then we're gonna do some partitioning, is actually coming, is actually just a soil evaporation. And then you see here that the CO2 flux mostly here is you have a positive flux, meaning that the soil is releasing CO2. Now, when the plants start to grow, you see different things. So you start driving the water use, the water use goes up, and also the CO2 uptake goes up until some point here in the mid-season, and then it starts to decline. So I want to call your attention to a period here during this data set. I think it's going to be helpful to understand what affect crop yield during this growing season. So you can see here this very high daily temperatures in this period. So it was like when you had those heat waves. Sometimes you see like temperatures here went above 40 degrees. I think you get a 118 one day in that station there. And then one thing that's interesting is that that temperature, since VPG is actually a function of temperature, you can see here like a very high VPG during that period. So that would cause an increase in water loss by the vegetation. And then what happened here is that you see that then we start plants starting shutting down. So you don't see much activity going on here. Like you don't see much carbon uptake, or it still has some water use here, but you see that the carbon uptake is decreasing, and then also the ET flux are decreasing for that period. So I use growing degree days, and then I said which period was that, and then this is actually occurring mostly during grain filling, the grain filling stage. So you can see here that when you come close, you see like very high. These are very high values for VPG driven by temperature, and you see here that the plants start to decrease ET and then decrease CO2 uptake because they just keep this stomates closed. So I talked to Justin about this, and then he said that this was one of the most promising corn fields that they had, and then with these heat waves, and then it really affected the yields. So I think he mentioned to us when you were taking the stuff out that I think he was getting, I think, 60 bushels per acre in this field. So as a summary here of the results is that the drought and heat stress during the grain filling period are likely to be the main cause for the corn yield reduction in the growing season. Another thing is that simultaneous measurements of ET and CO2 flux are important to understand the effect of environmental stresses on crops. And then another thing I was thinking, like maybe on the context of the rain project, is that these late season drought and heat wave events pose big challenges for adopting strategies to increase the resiliency of rain-fed cropping season, because they are really hard to predict because they occur in like several months after planting. So that's what I had, and then let me know if you have any questions.